Bueno, entonces hoy vamos a continuar viendo los videos 3 y 4 del curso Cómo funciona el Internet de Khan Academy. Entonces deben poner mucha atención porque van a resolver, finalizando los videos, unas preguntas. ¿Cuáles son esas preguntas? Del video 3 que vamos a ver, que se llama Paquetes, Enrutadores y Fiabilidad, vamos a responder cómo se transmite la información de un ordenador a otro. Otra, cómo se envía una imagen grande a través de Internet. ¿Cómo se llaman los dispositivos que actúan como gestores de tráfico en Internet? ¿Qué hacen los routers? ¿Qué es el TPC y cómo funciona? Listo. Y del segundo video que se llama HTTP y HTML vamos a responder. ¿Qué significa la sigla HTTP? ¿Qué significa HTML? ¿Qué hace HTML en las páginas web? ¿Qué son los cookies y para qué se usan? ¿Qué hacen SSL y TLS a las comunicaciones? ¿Y qué hace HTTPS? Acá en la última diapositiva les puse las dos direcciones de los dos videos que vamos a ver hoy. Ya les monté esta actividad en el modo para que la puedan resolver pues al finalizar la visualización de los videos. Vamos a empezar entonces de una vez con los videos. Vamos a ver el número 3 primero.
Hi, my name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. How is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there's no guarantee that every wire and computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet, a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it will be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits of ones and zeros, too many to send along in one packet. Since it's data on the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the Internet protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address.
Va a parar un momentico.
For the packet.
Sigamos.
Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly, horribly wrong. This is the basis for a key principle of the Internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgments of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the Internet becomes. What's also great is we can grow and scale the Internet without interrupting service for anybody using it.
The Internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the Internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the Internet. Computing devices, or routers along the Internet, help all the packets make their way to the destination where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the Internet talk to each other.
Listo, ese fue el primero de los videos. ¿Tienen alguna duda o continuamos con el otro? Bueno, ese silencio lo voy a asumir como una negativa ante las dudas. Entonces vamos a ver el siguiente video. Pongan mucha atención al final de este video porque van a mostrar finalmente un resumen. Listo. Ahí miremos qué me preguntaron. Todo bien, continúe, ponga el otro listo. Vamos a ver entonces este. Entonces, al final de este video, hacen como un resumen de cómo funciona todo lo que hemos visto hasta hoy. Listo. O sea, el resumen de los 4 videos.
I'm Jasmine Lawrence, and I'm a program manager on the Xbox One engineering team. One of our biggest features is called Xbox Live. It's an online service that connects gamers from all around the world, and we rely on the internet to make that happen. This is no easy task. There are a lot of things happening behind the scenes. The internet is totally changing how people interact and connect. But how does it work? How do the computers all across the world actually communicate with each other? Let's look at web browsing. First, you open a web browser. It's the app you use to access the web pages. Next, you type in the web address, or URL, which stands for Uniform Resource Locator, of the website you want to visit, like Tumblr.com.
Hi, I'm David Karp, the founder of Tumblr, and we're here today to talk about how those web browsers we use every day actually work. So you've probably wondered what actually happens when you type an address into your web browser and then hit enter. And it really is about as crazy as you can imagine. So in that moment, your computer starts talking to another computer called a server that's usually thousands of miles away. And in milliseconds, your computer asks that server for a website, and that server starts to talk back to your computer in a language called HTTP. And HTTP stands for Hypertext Transfer Protocol. And you can kind of think of it as the language that one computer uses to ask another computer for a document. And it's actually really pretty straightforward. If you were to intercept the conversation between your computer and a web server on the internet, it's mainly made up of something called GET requests. And those are really very simply the word GET and then the name of the document that you're requesting. So if you're trying to log into Tumblr and load our login page, all you're doing is sending a GET request to Tumblr's server that says get/login. And that tells Tumblr server that you want all of the HTML code for the Tumblr login page. So HTML stands for Hypertext Markup Language. And you can think of that as the language that you use to tell a web browser how to make a page look. So if you think about something like Wikipedia, which is really just a big, simple document, and HTML is the language that you use to make that title big and bold, to make the font the right font, to link certain text to certain other pages, to make some text bold, to make some text italic, to put an image in the middle of the page, to align the image to the right, to align the image to the left.
The text of a web page is included directly in the HTML, but other parts, images or videos, are separate files with their own URLs that need to be requested. The browser sends separate HTTP requests for each of these and displays them as they arrive. If a web page has a lot of different images, each of them causes a separate HTTP request, and the page loads slower. Now, sometimes when you browse the web, you're not just requesting pages with GET requests. Sometimes you send information, like when you fill out a form or type a search query. Your browser sends this information in plain text to the web server using an HTTP post request.
So let's say you log into Tumblr. Well, the first thing you do is you make a post request. That is a post to Tumblr's login page that has some data attached to it. It has your email address. It has your password. That goes to Tumblr's server. Tumblr server figures out that, okay, you're David. It sends a web page back to your browser that says, success, logged in as David. But along with that web page, it also attaches a little bit of invisible cookie data that your browser sees and knows to save. And that's really important because it's really the only way that a website can remember who you are.
Perdón un momentico.
And all that cookie data really is an ID card for Tumblr. It's a number that identifies you as David. And your web browser holds on to that number. And then the next time you refresh Tumblr, the next time you go to tumblr.com, your web browser knows to automatically attach that ID number with the request that it sends over to Tumblr server. So now Tumblr server sees the request coming from your browser, sees the ID number, and knows, okay, this is a request from David.
Now, the internet is completely open. All of its connections are shared, and information is sent in plain text. This makes it possible for hackers to snoop on any personal information that you send over the internet. But safe websites prevent this by asking your web browser to communicate on a secure channel using something called Secure Sockets Layer and its successor, Transport Layer Security. You can think of SSL and TLS as a layer of security wrapped around your communications to protect them from snooping or tampering. SSL and TLS are active when you see the little lock that appears in your browser address bar next to the HTTPS. The HTTPS protocols ensure that your HTTP requests are secure and protected. When a website asks your browser to engage in a secure connection, it first provides a digital certificate, which is like an official ID card, proving that it's the website it claims to be. Digital certificates are published by certificate authorities, which are trusted entities that verify the identities of websites and issue certificates for them. just like a government can issue IDs or passports. Now, if a website tries to start a secure connection without a properly issued digital certificate, your browser will warn you. That's the basics of web browsing, the part of the internet we see day to day. To summarize, HTTP and DNS manage the sending and receiving of HTML, media files, or anything on the web. What makes this possible under the hood are TCP/IP and router networks that break down and transport information in small packets. Those packets themselves are made up of binary, sequences of ones and zeros that are physically sent through electric wires, fiber optic cables, and wireless networks. Fortunately, once you've learned how one layer of the internet works, you can rely on it without remembering all the details. And we can trust that all those layers will work together to successfully deliver information at scale and with reliability.
Listo. Entonces, si ven cómo se produce todo el proceso de envío de información. O sea, miren todo lo que pasa detrás de enviar algo tan básico como una imagen. Entonces, quiero que me hagan preguntas si es que las tienen en este momento. Aprovechen antes de pasar a resolver las preguntas que les dije. Por ejemplo, ¿se acuerdan que cuando estábamos en el colegio nos pasaba mucho que iban a ingresar a una página y no los dejaba? Les aparecía ese aviso que aparecía ahí en rojito, que la página no era segura, que uno le daba omitir o le podía dar configuración avanzada y le podía decir que continuara, pero ya eso era bajo el propio riesgo de uno, porque ya le están advirtiendo a uno que la página no tiene, pues no está certificada. ¿Listo? Bueno, ¿ninguno tiene preguntas? Bueno, entonces les voy a mostrar las preguntas para que las vayan resolviendo. ¿Listo? Recuerden que yo voy a estar acá conectada por si tienen alguna duda adicional.